ठीक है गुड मॉर्निंग सबका आवाज
गुड मॉर्निंग।
आवाज म्यूट कर दो सब लोग का आवाज आएगा तो मैं बोल नहीं पाऊंगा। ठीक है, तो आज का जो टॉपिक है कंडेंसर एंड कंडेंसर टरबाइन वैक्यूम सिस्टम एक पार्ट है एंड एसोसिएटेड पार्ट इज सर्कुलेटिंग वाटर सिस्टम। तो आप लोगों का जो रैंकिन साइकिल और जो पावर प्लांट साइकिल डायग्राम वो हो चुका है मेरा ख्याल से। तो फंडामेंटल आइडिया व्हाट इज द सिमिलरिटी बिटवीन सेकंड लॉ ऑफ थर्मोडायनामिक्स, इसका स्टेटमेंट का मेन बात है कि वी कैनॉट प्रोड्यूस वर्क विदाउट एक्सचेंजिंग हीट बिटवीन टू रिजर्वायर्स, that is one is source. So source and sink, so we cannot make a work output without exchanging heat between two reservoirs, that is source and sink. That is source is boiler. In power plant source is boiler. We are providing heat from boiler and that heat is inserted into the turbine, that is the work and getting work output, and the heat rejected in the sink is condenser. So that is the condenser part, heat rejection. That is a modified Rankine cycle, simplified modified Rankine cycle. तो जो साइड में रिकॉर्डिंग है उसको हटा नहीं सकता तो आइकन अच्छा ठीक है। ये रैंकिन साइकिल्स है TS diagram. You know, everybody may be doing TS diagram. Our process is, this is pumping. We are pumping the water into the boiler at raised at higher pressure. That is the T higher pressure, boiler pressure. And heat is added. Heat is added in the boiler and the temperature is being increased to T1. So that is the source temperature T1. Right? So again, the steam is expanded in the HP turbine. Again, it is reheat is done up to the temperature T1 again, and it is expanded in LP and IP and LP turbine and condensed into the condenser. The condenser process is here to here. That means the latent heat is rejected Q2. So that is the Q2 rejected into the sink. That is the heat added is Q1 here, and Q2 is released in the condenser. So that is natural process and laws of thermodynamics we cannot avoid. We have to reject some heats in the condenser, otherwise it cannot be produced. The work cannot be produced. That is the similarity between, that is the Kelvin statement. We cannot produce work without exchanging heat between two reservoirs. So that is the basic fundamental similarity, and you can understand graphically well here. So that is the turbine output. What we can do? What we can do? We can minimize this heat rejection to increase efficiency. The Carnot efficiency we know. Carnot efficiency is, that is the Carnot efficiency 1 minus, that is T2 by T1. So that is the basic fundamental efficiency. So how from this efficiency cycle, so we can find out what is our idea. We have to increase T1 to minimize this factor. T1 means the source temperature. So higher the boiler temperature, the efficiency of the cycle will be higher. That is the fundamental idea we are getting from the Carnot cycle efficiency. And T2 is the condenser pressure. We cannot reduce much this. That is the obligations, but we can increase T1. So our main aim is to increase temperature T1 of the boiler, inlet temperature to the turbine, so that efficiency can be raised. So the source temperature can be raised and the sink is condenser temperature. So we have to reject some heat Q2. That is the second law depictions of cycle. That is source. Now come to the cycle. That is the theoretical cycle, modified Rankine cycle. That is modified Rankine cycle with reheat. It is the shaded area. Shaded area is the work output. If you reduce the condenser pressure somewhat little lower, so the work output will be increased, and so on. So the condenser pressure can be reduced or maybe increased depending upon the vacuum. This is the vacuum pressure. I told you this is the condenser vacuum. If you can reduce the condenser pressure, so the efficiency will be increased. So that's why you are maintaining condenser vacuum at a minimum value. What is possible, right? So now come to the cycle, main cycle. So it is, to recapitulate, the main cycle is there. This is the boiler. We are firing it, a schematic diagram. So the maximum temperature, the main steam is here. Main steam is coming out of the boiler and it is going to the HP turbine inlet with some valves, stop valve or control valve, as I said earlier. So that is the stop and control valve. The main steam is going over here and it is being expanded to a certain temperature. Suppose here, maybe temperature is 40 degrees Celsius. So here is temperature is much more. Suppose here is 540 degrees centigrade. The expansion is only 40 degrees centigrade, right? So now this steam is again goes to the reheater and is raised to 540 degrees centigrade. So this steam is going to, from here, it goes here, again from reheater it goes. That is the reheater process. HP turbine expansion and it goes to boiler. This is reheat. This portion is reheat here. So we are reheating in the boiler. Again we are reaching to the 540 degrees centigrade and that steam is going to the IP turbine. After IP turbine it is coming out and goes to the LP turbine. LP turbine, after expansion it goes to the condenser. Goes to the condenser. So condenser has a two function. Number one, it has to maintain a vacuum to increase efficiency. Number two, the steam will be condensed to water and it will be storage in the hot oil. That is called a storage place below the condenser, that is called hot oil. So the water, once it is condensed, the steam is being condensed over here by circulating water. So this water again is being pumped by some pump and it is goes to the, again goes to boiler. Again we are feeding into the boiler. So that is the cycle we are going. In between there are a lot of things are there. We are not going much detail about it. So very simplified is, now you can similarity, you can match this figure. Here HP turbine inlet, HP turbine outlet, reheater, IP turbine, LP turbine and condenser. This is the condenser. The latent is being rejected into the CW system. The heat is rejected over here. That is the latent heat. The steam is being condensed to water. You know this is the Rankine, that is the water diagram, TS diagram, properties of water. This is saturated water line, that is saturated steam line. This is critical point. So that is the fundamental water properties. So the steam is being condensed to water over here. This water again pumped to boiler and heat, parallelly heat is added. So that is the process of modified Rankine cycle, theoretically and practically it is here. I hope it is clear. So now the condensation, how turbine vacuum is created. That means here should be minimum pressure. At the last stage of turbine, LP turbine, the vacuum should be maintained so that the efficiency is there. That means it is connected to here. What is the pressure over here? That pressure is same pressure at the outlet of the LP turbine. That means we have to provide some line over here. Condenser vacuum. How the vacuum is being created? Suppose steam is here, like at low pressure steam volume is like this. By any means, this steam is become condensed by cooling it down. It will be reduced to like this much volume of water. This is water and this is the steam. Same amount, suppose 1 gram of steam is being condensed into 1 gram of water. So the volume occupied by this steam is reduced to this. If it is a closed space, what will happen? The space will be vacuum. That means the pressure will be lower. So that is the fundamental idea. Once you provide some circulating water, right? That is the raw water we are providing in the condenser for thousands of tubes, and it is circulating, and steam is passed across these tubes, cross flow. So heat of the steam is taken out by the heat exchanger, that is condenser. That heat is taken out by this water. I can suppose 30-degree inlet and 38-degree outlet temperature. So 30-degree centigrade water is entered over here and taking the heat, the temperature raised to 38 degrees centigrade. So that water is goes to some tower. We have seen the cooling towers where we cool it down the water naturally. That means it goes through the pipes. Suppose this is a pipe, and pipe is along the length. Pipe is distributed and water is being distributed in the tray. This is the tray. Both the side the water is distributed, and there are thousands of holes are there. By this hole, water droplets is coming out over here. Water droplet is coming out from the top, and this hot water is coming through droplets. Some fans are rotating over here. That is called cooling tower fans. Cooling tower fans are rotating over here. It is sucking the air from the perforated area beside this. So air is being sucked over here. So that means water is falling down. Yeah, water is going up. So what will happen? From the surface, the heat is being taken by the air by evaporation. The principle of cooling in the cooling tower is, suppose this is a droplet, some amount of water being evaporated from this. So what will happen? The latent heat will be taken from the droplet itself. The latent heat from the droplets will be taken out by the evaporating water, which will go and it will be evaporated from this place. So that means the water droplet, by losing some water vapor, the droplet itself getting cooling down. So it will fall down to the tray below here. So that means the evaporation, the fundamental idea of natural water cooling is, suppose this is 38-degree water, and when it is falling down over here, it becomes naturally 30 to 30 degrees. It is again going to the series of pumps, that is called CW pump. CW, what is circulating water. CW means circulating water pump. That 30-degree temperature water again being circulated through this line, and it goes to the condenser, and it is taken heat from the condenser, and the steam is being condensed to water. So this cycle is the generation cycle. That is, the steam is becoming water, steam become water, that is DM water, demineralized water. But this is the raw water which is going through the pipes. Inside the pipes, thousands of pipes, it is not being in touch with this steam. That is surface condenser. So that means this water, 30-degree temperature, this is going out at 38-degree temperature with heat exchanger. That is mechanical design part. We are leaving about it, LMTD and other terms. So we are taking the heat, and it is water is being condensed. The same DM water, the costly DM water, which is manufactured at the rate of 12 rupees per liter, that's water is recovered here, and again it is being pumped to boiler to make steam. The same water is circulating. If there is any losses, so loss is given by a makeup water in the, suppose 2 to 3% is loss, is practical losses are there. 2 to 3% water, steam is being lost, so that is fed into the condenser. Water is fed into the condenser to make up this circulating water. For a particular power plant, suppose 210 megawatt power plant, the water requirement is, the steam cycle in the requirement is 570 ton per hour. 570 ton steam should be, or water to be circulated around the cycle. So according, if this water is becoming less, then the power generation will be less. So we are maintaining the flow rate at 570 ton per hour. And similarly, roughly it is a 3 time. Suppose it is a 800 megawatt power plant. So for this, around 2400 ton per hour water should be circulated in the cycle. But this is the cycle. It's called CW system, circulating water system, which is heat is taken out, the steam is being condensed. By condensing the steam, now already vacuum is created in the condenser. That is the condenser vacuum. How the condenser vacuum is created? Not by the so some vacuum pump is also connected over here or ejectors. What is the function of ejector? Function of ejector or vacuum pump is to remove the non-condensable gases. When steam being condensed over here into the water, some amount of oxygen or air is there always. So continuously steam being condensed, continuously small amount of gas is coming out. If it is not being taken out continuously by vacuum pump, so what will it fill the space and the vacuum will be reduced. Once the vacuum will reduce, the efficiency of the, that means this line will go up. If vacuum is reduced, this line, condenser line will go up, so output will be less. That means your turbine performance will be less. So vacuum is so important. The condenser pressure is maintained is around 0.1 kg per centimeter square. 0.1 kg per centimeter square. What is 0.1 kg? Where 1 kg is the atmospheric pressure. 1 kg per centimeter square. If in a barometer, if it is atmospheric pressure, 1 kg. So if it is absolute vacuum is 0 kg. So that is the condenser vacuum. We cannot. So that is the zero level. That is 1 kg atmospheric pressure. So we are maintaining condenser pressure level at around this 0.1 kg. That is right. So minus point. If you say it below atmospheric, it is minus 0.9. If you consider it 0, it is minus 0.1 plus 0.1 is minus 1. If you take the atmospheric pressure 1, so we are maintaining condenser pressure at this level, right? Minus 0.9 or absolute pressure 0.1 kg. So that is the amount of vacuum to be maintained. Vacuum is maintained by vacuum pump or ejector, but vacuum is created by this condensing steam. Continuously the steam is being condensed, the vacuum is created. But vacuum will fail if you stop removing the non-condensable gases. If you don't run this vacuum pump or ejectors, the vacuum will not be maintained. So vacuum to be maintained by this, whatever the by condensation vacuum is created, that should be maintained by your vacuum pump or ejector. That is the fundamental of turbine vacuum system. And also for vacuum system, we are sealing this point because shaft is rotating over here, casing is not rotating, turbine is rotating, casing is rotating. The steam between this passage, steam will go out. High pressure steam will try to go out from these passages. So that passage is being sealed by giving some external steam. So that is called gland sealing system. So gland sealing, if you expand this portion here, it looks like this. This portion is here. It looks like this. Suppose this is the casing part and this is the rotating turbine. It is rotating, the rotor is rotating, the casing is not rotating. High pressure steam is over here, it is trying to go out. If the pressure is very high, so we provide 5, 6, 7 part of restrictions. Restriction is simple ring type things are there. The passage in between is very less. So that the Joule-Thomson effect workers, the high pressure steam, once it is throttled over here, the pressure becomes very less. Suppose 140 kg, it may be around 30 kg. Then maybe it is 5 kg, 1 kg, like this. If number of restriction is more, the steam will be throttled. The pressure drop will occur. The pressure drop will be so less that last one stage, we provide some external steam at 1 kg, so that this steam will not be lost. So if you provide some lost steam over here, and some drain system is there, and it is being collected and it is going to condenser. Again, the gland stream which is provided for sealing should be drained over here. Some draining system is there, so that we are providing leakage of high pressure steam from the turbine by providing sealing system. Sealing is not, it is a metallic part. Rings are metallic, very restricted passage in between moving and non-moving parts. Non-moving parts are this casing and moving parts are sub. So that is being sealed by the gland sealing system. So there is sealing, there is a sealing, and sealing. Here sealing. Whole part is being sealed by your gland steam system. There is a pressure we are providing the gland steam at a pressure of 1.03 kg per centimeter square. So we are preventing any steam leakage from the turbine and outside the atmosphere. In some other cases, here it is, we are preventing air to ingress, because here is low pressure, below atmospheric pressure is air. So air will try to go inside the turbine. So here the sealing purpose is different, to prevent air ingress into the turbine. Because if we ingress air, what will happen? It will mix with the steam, it will come here, it will reduce the vacuum. So to maintain the vacuum, sealing is important. Here sealing is to prevent losses of steam. Here sealing is required to maintain the vacuum, otherwise the efficiency of the turbine will be lost. So that is the turbine vacuum system, and that is CW system, that is